So thank you. I guess if there are no more questions, okay, wait just a bit to see if something shows up. Michael, fascinating. Thank you. It's not a question, but it's a good it's a comment. Very good comment. Yeah, it's very interesting. Very, very interesting. Yeah. Okay, so thank you very much, Vincenzo. Thank you very much.
Grazie, grazie, grazie.
Ciao. Bye. So the next speaker is Diego Giusia. Who is that guy? I'm afraid I think we are going to talk about frogs and toads. Diego.
Can you hear me?
Yes, I can.
Yeah. Great. Okay, I'm going to share the screen. Okay, thank you, Jerome. Hello, everyone, and thank you for attending the presentation. I know that you are probably quite exhausted after 3 days, well, let's get started. This is me when I started my PhD, and at the time we needed to produce our own automatic recorders to monitor frogs, birds, and so on. But nowadays it's much easier. There are a lot of different options to perform passive acoustic monitoring in terrestrial environments. Since 2007, there are commercial devices available, and this field has progressively evolved quite quickly. The technology now has changed a lot, and recording sounds from the environment with acoustic devices is much easier now than in the past. So recently we wanted to quantify this change, how the evolution of the technology has influenced our field. As Larissa Sugai saw yesterday, in a series of literature review, we quantified the number of studies using this technique, and we saw that acoustic passive acoustic monitoring is an emerging tool in ecology and conservation, as you can see here, and has been used for multiple subjects and applications. And I wonder if we can use also this tool for climate change research. We can add this additional subject to the list. Well, this is the specific question I want to address in this talk. Can acoustic monitoring help us to better understand how the species cope with climate change? Of course, there are different alternatives for this purpose, and I will focus on a particular approach, which is the species distribution models. As you know, species distribution models are a standard in climate change research. They are mathematical models that are able to estimate the species' capacity to survive and to respond to past or future scenarios. And author has described at least two types of models. First, correlative SDMs, which are based on observational data, basically a species occurrence. That combined with environmental information can produce these predictions. Well, these models are quite common in research. They saw several advantages. For instance, the large amount of data which is available. Also, they can be considered ecologically realistic, since data come from natural conditions. But also, they receive some critics. For instance, they estimate the realized niche. It has been proposed another model, for instance, the mechanistic, or also called process-based models. that use experimental data to produce these models, this estimation for the future or even for the past. So this mechanistic model try to improve predictions by estimating, for instance, the fundamental needs. They use ecophysiological information at individual scale for particular traits, but also we can see some constraints, some limitations on those models. So here we propose an alternative or complementary, I would say, but a complementary method, which is ecoacoustic models. Bringing together two disciplines, ecoacoustic and biogeography, we want to propose a new tool, ecoacoustic SDMs, based on data coming from passive acoustic monitoring. The purpose, the goals of this tool will be to project our acoustic data into larger scales in order to improve our prediction on how species deal with climate change, particularly, obviously, species that communicate by means of sounds, and also to try to see, to estimate potential shifts in the environmental suitability for performing, for the species to perform this acoustic communication. To make this possible, I developed a project called SoundClean, thanks to the fund provided by the European Union. I started to work with a few experts on modeling macroecology, Sara Villen Perez and Paulo de Marco from Universidad Federal de Goiás in Brazil. And additional funding helped us to add a new member to the team, the unique and the great Camille de Jonker, who helped us a lot to update, to improve our first framework. And she finally, performed the final analysis. I'm going to show you here. We develop and test this methodological tool using data we collect during my PhD under the supervision of Rafael Márquez and Juan Francisco Beltrán. Specifically, more than 3 years of data for 10 populations associated with 5 species, 5 Iberian and Uran species. So how does it work? Well, this framework is composed by 5 basic steps. First, we need to identify population located at the climatic extremes of the geographic distribution of the species, so that we can capture, we can take into account the whole range of climatic variability that the species are exposed to. Then we can monitor those populations over long periods, at least I would recommend 1 year. And then, of course, analyze all the recordings using manual or automatic methods to try to get a data set like this one with a time series of data of a species activity, presence or absence of calling activity associated with local weather conditions. Then we propose to calculate an easy response variable, an index we call calling probability, which is as simple as the number of recordings with presence of calling activity divided by the total number of recordings. This how probable is that we found an calling event in our time series of recordings. Once we have this for a particular period of time, for instance, per month, we can fit our model using this response variable against a series of environmental predictors. So what we get when we fit the model for our study species, we found that all predictors that we use significantly influence calling activity, factor associated with temperature, precipitation, and photoperiod, but in a different way depending on the species. So we saw that each species was related in different way with climate, with the local weather conditions. Once we have our models, we wanted to validate potential predictions we are going to generate with them. So what we did was a validation processes, splitting in an iterative loop, splitting the data set, and then calculating predictive values that we could compare with observed values. As you can see here in the plot, we got very promising results actually for all the species. Observed values, observed calling probability was highly correlated and positively correlated with predictions. So we can conclude that our models for these species have a high capacity to predict calling activity. So now I'm showing you the first example of the prediction that we get from these models. In particular for 1-tree frog species, using an average climate scenario for 2070. So here we have the suitability of the difference between future suitability and current suitability for calling behavior in the different months of the year. So as you can see here, all the values are positive, meaning that the species will found, according to our predictions, better conditions for calling behavior in the future than in the present. So some improvements in the condition, particularly in the middle of the year. So now we can, once we have all the data to see this geographical shift in conditions, we can sum up everything, summarize, and make an average, and to see the whole picture, the general change from future to from the present to the future for this species. But this general improvement for the tree frog was not the case for the rest of the study frogs. As you can see here, we get also negative values in blue for other species, meaning that we predict important declines in the climate conditions for calling behavior for those species. Here you can see the polygons representing the species range. So our models predict the species-specific responses to climate change, as you can see here. To put it in a more clear way, we can see this figure. We calculate an average and variation for the whole range of the species, calculating the suitability for calling in current conditions, but also in the future conditions in red. So as you can see in this graph, for two species, we predict important declines in the condition. These species are species having population and in mountain areas, while lowland species, we predict no change for them, for the conditions for them, or even improvements. And finally, we can also try to understand if breeding phenology could shift due to climate change. So here we average all the values divided by months. So this number you are seeing here are the different months for each species. And the area represents how suitable are the conditions in the present, in blue, and in the future, in red. So for instance, in this right panel for Alites dicyleni, we can see that the conditions are shifting towards the beginning of the year. So we predict potential advances in breeding phenology for this species, while other species show probably a stable breeding phenology in the future, according to our models. So these acoustic models are not going to solve, of course, all the problems that we consider as a valuable tool, a valuable contribution to shed light in this line of research. In general, can be considered as correlative models, as they use observational data, so similar advantages and disadvantages, but also they provide some improvements that we think that approach them to mechanistic models. First, they are focusing on calling behavior. That means that the predictions we are getting are biologically relevant. The implication of our predictions are quite important in terms of physiology and ecology, because, as you know, this trait, calling behavior, is closely related to reproduction and individual fitness. Also, our sampling is able to improve the temporal scale of the data. We are not only seeing present absence of a part in a particular site, but how a species is responding across the year to climate conditions. And this give us higher resolution in the association between climate and species behavior. So altogether, we think and make this tool quite useful, especially for forecast phenological shifts. So to sum up, we think that acoustic monitoring can efficiently assist climate change research, especially using this tool we developed to forecast the potential species response to climate change. In particular, we forecast temporal and spatial shifts in environmental suitability for calling, although with species-specific responses. And we are expanding our project to a new country, to Brazil. So we are using SoundClean there to build a new monitoring network, and we are now helping help with many different researchers. We can monitor around 35 sites there, and we hope in the future we can show you data for neotropical species. So I want to end here just to remind this paper by Molonino, Pijanowski, and Gass, with an appealing title, The Silence of Biogeography, where they pointed out the less attention paid by biogeographers to natural sounds. And we hope that with this new tool and other approaches, we can start to fill this gap and to bring sound to biogeography and climate change research. So I want to thank all the people involved in these projects, and also to you for your attention. Thank you very much.
Thank you very much, Diego. Very nice and clear research as usual, I would say. So there are plenty of questions. I start with some in the chat. The question: how did you calculate calling rate for each frog? Thank you, for Natalie Sanchez.
Well, thank you, Natalie. It was a very good question. Actually, we can say that the model focus at population scale. So we are not measuring the response of a particular individual as mechanistic models do. We, as you know, probably when we are recording the sounds from a chorus, from a population, we don't know exactly who is singing there. So we are measuring the response of the population in our monitoring site and not individual. So we cannot get individual data using this acoustic monitoring. Unfortunately, maybe in the future we can, but not yet. Not yet. We are this is a populational scale analysis, let's say.
Okay, so there are plenty of questions. Klaus is saying, I vaguely remember some climate change models predicting Spain might be a desert in 2070. And then he adds, sounds like global amphibian decline, not a problem in Spain, question mark.
Hopefully not. Those predictions are not reliable. Let's see. I mean, of course, for this particular organism, changes in precipitation are going to be dramatic. Actually, we published a few papers trying to predict how the species responds to changes in temperature, and it seems that frogs are quite plastic and quite tolerant to changes in temperature, much than to change in precipitation and rainfall. So of course, it's going to be key how this is going to change in the future.
Yes, actually, you make a connection with Dan's story question, who asked, would plasticity of vocalizations affect the correctness of your predictions? It seems you have to assume the observed vocalization are the same as would be used in the future.
Sure, it's a super key question here. Thank you, Dan. Actually, as I said, these models can be, are similar as correlative model. And one of the limitations of correlative models actually is that they are not generalizable to novel climates, because we are making prediction based on observational data. So as you said, we need to assume that the species are not going to change in their response once the climate change, because this is something that we can only estimate by making experiments in the lab. That's what mechanistic models try to do, try to estimate fundamental niche and not the realized niche. So we still are close to correlative models in that sense.
Okay, thank you, Diego. We should stop if we want to have some coffee break.